say you wanted to add 2 alcohol groups, but do them syn addition. So here is our syn addition reagents. No mechanism here. Just like the previous syn addition, these reagents add the 2 alcohol groups concerted. There'll be a concerted first step where those 2 sigma bonds are added at the same time. And so that's why we see syn addition here. Again, that is a stereoselectivity. No regioselectivity here either, because we see 2 OH groups. So there's no way to know which ones adds first or second. And so when we're looking at these, we have 2 options. KMNO4 is a reagent that is potassium permanganate. It's an ionic compound, and so it needs to be in an aqueous solution. That aqueous solution is normally basic and held cold because this reaction is more exothermic. And so the second option is osmium tetroxide. Osmium tetroxide is an interesting reagent. It is used only here as a secondary reaction since a lot of organic molecules don't like to dissolve in water. But osmium tetroxide is very expensive and it is very toxic. And so both of these are fine reactions. What I would want you to be able to know is just looking at the reagents to know what they do, not how they do it. So no mechanism there. Last reaction is ozonolysis. I know we've moved really fast on these last couple ones, but that's because these last ones, we don't have too much of a mechanism for them. It's more of a reagents and a predict the product style question. For ozonolysis, what's really important to note is that ozone, O3, is highly reactive and it breaks not only the sigma bond, but also, or not only the pi bond, but also the sigma bond in these reactions. And so what we get out of these reactions, and I'm going to try to draw it so that we can see where that came from the actual double bond itself. We get a complete separation of our molecule and a full oxidation, creation of aldehydes and ketones here. A good rule of thumb for this reaction is you split the carbon-carbon double bond and you will put on one side an oxygen and the other side an oxygen. I like to put in the hydrogens for these aldehydes just to be able to see they were there to begin with, but we usually just don't draw them in. You don't have to draw them in, they're just there for fun to make sure that you can visualize all of the octet of those carbons. Again, transformative, there's no stereoselectivity, no regioselectivity. Carbon 1 and 2 of the carbon-carbon double bond are still sp2 hybridized. Two-step reaction, we use ozone first, and then DMS, dimethyl sulfoxide, sulfide is a reagent to use in step number 2 to clean up that excess ozone. I like this, we'll practice with this spider diagram idea in class together, but these are all the reactions that we just learned. A lot of them we had mechanisms for. I want to go through that. The addition of HX, Markovnikov addition, when we add H3O plus, those 2 are the Markovnikov additions where we see carbocation intermediates. Very similar to that, we had oxymercuration, and that is a Markovnikov addition, but without a carbocation rearrangement. Then we had our anti-Markovnikov, which is our concerted reactions with hydroboration oxidation, followed by our hydrogenation. Another anti-addition along with our oxymercuration was halogenation and halohydrogen formation, right? And we also had our anti-dihydroxylation, which I also call epoxidation, followed by the acid catalyzed epoxide opening. And then we had our syn additions, where we added two alcohol groups to the same side of the double bond, right? All of these are really important to just understand their stereoisomer format. And then ozonolysis, no mechanism for that, no stereochemistry for that. We split open the sigma and the pi bond there of the carbon-carbon double bond, and we put double bonded oxygens on either side. We will come back to HBr and ROR, HBr and peroxide. Just note that that is an anti-Markovnikov addition product. Okay, let's talk about synthesis. Synthesis is something that an organic chemist does in real life to understand how to design a product to create some desired molecule. We actually need to predict the reagents necessary to transform a reactant to that product. So synthesis is all about taking that step and linking a product to a reactant. So we kind of do a retro analysis. Now, retro meaning the idea of vintage or backwards in time, right? Thinking about retrosynthetic action, meaning going from the product backwards to the reactant, so that we really ask ourselves, how do we make this product? In order to do synthesis successfully, you have to know all of the tools in your toolbox. Every single reaction, every single transformation, you should know well. If you are struggling with the forward, take a step back and make sure you practice the forward reactions, because asking you asking yourself, how do I make an alcohol? Well, if you don't know the forward reactions on how to make that alcohol, you can't step backwards and say, well, what molecule made that alcohol? And so that's what we're going to practice today. Again, if this is a struggle, take that time to learn the forward reactions well. Each individual reaction that we have seen in these previous chapters will be valid on synthesis problems. All right, we want to ask ourselves two questions to link the reactant to the product. Looking at this first example, we have an alkyl halide on the left, the reactant, and we have an alcohol on the right. So let's ask ourselves, did the number of carbons change? I'm going to do a quick count. No, the number of carbons didn't change. A couple of good things to note with that number of carbons: ozonolysis breaks apart carbon-carbon bonds. So if you see a decrease in the number of carbons in your organic molecule, it's usually because of ozonolysis. So that's a good one to remember, right? We can also think about increasing, right? This is for a decrease. We have seen an increase, which was with our Cn minus SN2 reagent, and that would increase the actual number of carbons that add on that one extra carbon, right? So thinking about things that have added or decreased carbons in an organic molecule is very important for us. The second thing to focus on is the functional group. If you are struggling with identifying functional groups or naming functional groups, take the time to go back. This was in chapter 2, so it would be really important to be able to communicate what functional groups have changed, so that you can try to really hone in on the reagents that introduce that functional group. So here in this example, I see that a halogen has been changed to an alcohol. But this isn't your typical SN2 reaction, because we do see that the position of the alcohol is different from the position of the actual halogen. And so taking a minute to say, let's do some retrosynthetic action, all right? I'm going to go ahead and scroll down here and say backwards arrow. There's my retro arrow. That's not a forward reaction arrow, that's a backwards reaction arrow. How do I make alcohols? Well, I could think about an SN2 reaction, or right in the forefront of my mind, alkenes with H3O plus would do the trick, right? Acid catalyzed hydration. Well, okay, how do I make an alkene? I can make it from an alkyl halide via an E2 reaction. All of these notes are really helpful for us to be able to identify and link the reactant to the product. So I did some notes on some retrosynthetic action. Now to go forward, how do I actually take this primary alkyl halide and transform it to that secondary alcohol? Step number one, let's throw in a big bulky base. You can use H minus, right? Hydride is a great E2 reagent. You could use DBN, DBU, anything that was valid to make E2 the major product here, right? We have a primary alkyl halide, so it likes to form substitution. I don't want it to substitute. I want it to eliminate. So make sure in that first step you have a large bulky base. Step number two, you take that resulting alkene and you perform acid catalyzed hydration. Carbocation intermediate there, it will form our product. No carbocation rearrangements for that one. So let's go ahead and just do that forward reaction. Alpha and beta here, we have our large bulky base. We'll do our E2 proton transfer with the loss of the leaving group and acid catalyzed hydration. We'll go through this. We just did this reaction, so hopefully it's still fresh in our minds. Proton transfer followed by the nuke attack and the final proton transfer to get that protonated alcohol to be neutral. You never have to go through the mechanisms on a synthesis. Really, the only things that are required are the actual steps. But I like at this point to double check our work to make sure our work makes sense. But notice what's highlighted in that yellow box is the only thing that would be graded overall. All of this is notes and verifying that I did it correctly. Let's do it again. All right, did the number of carbons change? Don't forget to count that one. No, the number of carbons don't change, but my location changes for the bromine to the product alcohol. So what again do we want to think about? How do I make an alcohol on a less substituted center? That's a great question. Without going through a carbocation intermediate, hydroboration, oxidation. BH3 with THF. This is a two-step reaction. We need peroxide and sodium hydroxide, any order for that second step. Two isolated steps, right? Two sets of reagents there. Now, that's how I can take an alkene to a less substituted alcohol. Well, how do I make that alkene? Specifically, a Hoffman alkene. Again, large bulky base, something that is in the E2 category, but preferencing Hoffman over Zaitsev, we do have two beta carbons and two beta hydrogens, therefore, in our original reactant, so be very careful. Again, these are all notes. What we would want to be able to think about is putting it all together with the reagents going forward. We think backwards, but then when we actually answer the question, we got to go forwards. We want to start with that E2 and finish up with hydroboration oxidation. Notice this one is a 3-step reaction. 2 overall reactions, but again, 3 steps to those reagents. Take the time with synthesis. We will be practicing synthesis throughout the rest of our time together. It's very important to be able to understand these steps, noticing all the tools in our toolbox, so that when you, on an exam, are given a multi-step synthesis, you too can step backwards and ask yourself, how do I make that specific functional group? Do I have any changes in carbons? Where's the functional group location? Things like that. The more intimately you can understand these molecules and you're not afraid of them, dive into them, pick them apart, number them, take the time and practice the forward so that the backwards reactions, the retrosynthetic action, can be easier. So your synthesis questions are more straightforward.